All right, great question here to link the idea of atom packing in molecules and density. And so we're going to use this density formula we learned in class. Now, if you look at the review of what ALEKS tells you, it'll mostly focus on, and it'll say P, and it'll use this formula here. Now, that's what we started with. I used the big D, and we started with that. Now we took that one step further. We used that same N, and then we used molar mass, which is grams per mole here. And then over that was this A cubed times Avogadro's number, which is at 6.02 times 10 to the 23rd, whatever per mole, right? And so we're going to write it as per mole, which will cancel with the molar mass. And now we have this A, which we're given in this problem, right? We're given an A here. Now, moles will cancel and we'll be left with grams per A cubed. So the question asked for it to be in centimeters cubed. So we're going to need to put A in centimeters. And right now it's in picometers. So we have some conversions to do there. And then we will stick with this formula, and then making sure we're careful on what N is, right? We covered two different things. We covered BCC, which was this, not the best artist here, but where we have the atoms on each corner, and then we have one in the middle. So we get that 1/8 of each atom on the corner times 8 of them equals 1, and then plus 1 in the middle. So we have N equals 2. And then we talked about FCC, which is a little more crowded or better packed. You still have those 8 on the corner. And then you have half of 1 on each surface. One there. So we have that same 1/8 times 8 plus 1/2 times 6 surfaces and 3. So we get N equals 4 with an FCC. Now this one is saying it's FCC, which is better packed than BCC. We saw that periodic table that showed some of the elements. There's not really a rhyme or reason looking at the periodic table like we saw last term with a lot of those trends. So that is something we'll tell you. And notice in here, we're looking at FCC or BCC. So this is the FCC one. So let's clear this out and give this a shot here. Okay, so we saw N equals 4. We're going to do the molar mass of iron, which is 55.85 grams per mole. Then I need A. Now that's going to take some conversion. So I have 352 picometers. I'm going to convert, I don't know the conversion from picometers to centimeters, so I'm going to go out of picometers into meters and then out of meters into centimeters. I know this is 100. I know that for every 1, there is 1 times 10 to the 12th picometers. So we got to do this conversion, and then we will cube it to get that centimeters cubed. Okay, so 352 divided by 1. I'm going to use that EE button to the 12th and times 100. So I get 3.52 times 10 to the negative 8 centimeters. Now that's A. So to get A cubed, I do 3.52 times 10 to the minus 8. And I cube that. And I get 4.3614 times 10 to the negative 23rd centimeters cubed. So we put that in. And then I'm going to multiply it by 6.02 times 10 to the 23rd. So that will cancel out most of that, which it should be a number, you know, within a few orders of magnitude of 1. So let's take a look. For any sort of molecule, and especially an iron, so we're not looking at gases here, we're looking at solids, so it should be in the, greater than 1. Okay, so 4 times 55.85. Now I'm going to divide it. I'm going to use parentheses here, 4.3614 EE negative 23 times 6.02 EE 23. And I get the density is equal to 8.5087 grams per centimeters cubed. Now I see 3 significant figures, so I'm going to say 8.51. There we go. Okay, so using this formula is the key, recognizing if it's FCC or BCC, and it really gives us this link of, right, how well an atom packs, its molar mass, and how that applies to density.